Properties of solids. So the difference between a solid, liquid, and a gas of the same molecules, the difference is how strong the intermolecular forces are. Strongest intermolecular forces is going to result in a solid. Weaker intermolecular forces is going to be a liquid. And then no intermolecular forces, or very few, is going to be a gas. So the reason why things stay as a solid and stay locked into that fixed volume and shape is because those intermolecular forces are holding it together. As those intermolecular forces weaken, typically the reason why they weaken is due to heat or thermal interference. As they start to weaken, then they're able to slide past each other, but there's still some attraction there, okay? So they're able to keep their volume, but they can't keep their shape. When those intermolecular forces weaken or are gone completely, then those molecules aren't attracted to each other and they're able to spread as far and wide as the container allows them. And that's when you have a gas. That is the difference between a solid, liquid, and gas, is the strength of those intermolecular forces.
Yeah, solid. Big.
Okay. Now, there are 4 basic types of solids. We have an ionic solid. We have covalent network solids. We touched on that briefly yesterday. You are familiar with molecular solids such as glucose, for example. And then there are metallic solids. Solids then are classified by what components occupy the lattice points. A lattice is a 3-dimensional system. It's kind of like a scaffold. If you've seen scaffolds outside of buildings when they're, or even inside when they're working on walls and stuff. Well, they usually have like cross beams, and they have a platform that people can stand on and do their work and stuff, but they're temporary, These are always there unless, the thing ends up being melted. So these have these lattice points, and that is where they're going to be connected by either attractions or bonds. Many properties of these solids are determined by the strength and type of intermolecular forces present. So for ionic solids, that is the structure of the solid. It's those interactions, the attraction of the positive and negative forces. And we can look at Coulomb's law to kind of guide us and be able to tell the difference between the strengths of different ionic solids. Collectively, all ionic solids are known as salts. So not just the NaCl that you're familiar with, but any ionic solid in chemistry is called salt. So it's kind of like being down south. You ask for a Coke or a Pepsi down there, and they ask you what kind. And they're not talking about diet or not. You would respond to them, oh, I want a Sprite, or I want a 7-Up. Just like, oh, you have a salt. Oh, is that NaCl? Is that BaSO4? Is that, So yeah, down south, if you ask for a Coke, they will ask you what kind.
Like Coke brand.
No, it doesn't even have to be Coke brand. It could be A&W root beer. They collect, instead of calling it pop down there, they call it a Coke. Yep.
Yeah, instead of calling it soda.
What if you said what solid?
Then you would tell them I want a Coke.
Would they be like, what one?
No, they would just say, okay, I'll give you a Coke.
You said any what solid?
Any ionic solid is known as a salt.
Is this ceiling tile new? The one with, oh wait, yeah, you can't paint them anymore. Which one? I don't know if I understand that.
Which one?
The one with the paper.
They tend to be brittle. That is due to the repulsion of like charges. So this was one of the questions that you had on a recent test. And the reason why that works, are you not going to let me write on here?
Okay, I have a question.
Are you going to let me write? Oh, you are. Good. What? Yes.
She was asking what
What? Oh, brittle.
Yeah,
Easily broken. Yeah.
That's what I thought.
Okay. So when these things are together, they're attracted by plus and minuses. Okay. And it's an alternating plus and minus. If we go in and we try, if we manipulate these in any way, trying to bend them or shape them, what's going to happen is these like charges are going to line up. And what do we know about like charges? They repel. And so this will end up breaking here, and that's why these are brittle. As opposed to like a metal that if we tried to pound that out, it would just flatten because of the sea of electrons. It would be able to kind of be manipulated that way. These would just crumble apart. So if I just took salt and I grind it, okay, it's going to grind out. As opposed to metal, if you applied, a significant amount of pressure, it would just flatten out.
Okay.
Rather than breaking and kind of shattering into pieces.
Okay.
Covalent network solids, again, we touched on these some yesterday. These tend to be very large molecules. They're formed from non-metal elements such as diamond, graphite. Remember, the difference between those is how that carbon is arranged. In addition to that, there are two other nonmetals, the silicon dioxide and silicon carbide. These are the ones that they will touch on in your AP tests. There are other ones out there in existence, but these are the ones that you need to know.
What about C60?
I doubt that would be on there, but you would recognize it.
Buckyball. They're banned. Banned.
To melt these covalent network solids, the covalent bonds have to be broken. Covalent bonds then are pretty strong. And so typically they're going to be hard and you're going to have very high melting points. The three-dimensional network solids then are very rigid and brittle because the covalent angles are fixed. That's why they're able to take diamonds and be able to cut them down into smaller diamonds. Okay. That's how they call those fracture lines. So they're able to find where these lines are, and then they can break it on those. And the really good diamond experts are able to craft these into nice, looking things. Yeah.
Yeah. We watched a video on it.
Carbon-containing covalent network solids. Carbon is the basis for biological compounds on this planet anyway. Well, they haven't found life on Mars, so we're not sure. Okay. I don't know.
What?
There's a planet where when it rains dust. I think it's Venus.
Why don't we go visit?
Their planets.
It's very inhospitable. It would be very hot there too.
I hope it's Neptune. I like Neptune the most.
That'd be cold.
There's
All right.
one that rains acid.
Diamonds then are carbons. They're going to form these tetrahedral shapes and these three-dimensional networks. They're going to be basically colorless, or at least you're hoping. If it's, well, there are some diamonds that are different colors, and then they cost different amounts. They tend to be insulators and then high melting points. No, I think pink diamonds are like more expensive because they're pretty rare.
Yeah. I like black opal better.
Graphite then is your carbon atoms, and these are going to form two-dimensional network solids. They're going to be layers, and remember those layers are what you break off as you're writing on your paper. Okay. Silicon-containing network solids. These are your silica, which is mostly sand. That's what your sand is. Glass. Glass is actually an amorphous solid. Remember, amorphous solids are able to change shape over a long period of time. And that's why, Yep, they'll warp over time because they don't have that set structure. And then silicon carbide is the only chemical compound of carbon and silicon, and it is an excellent abrasive.
Is that what's your favorite covalent network solid?
I don't know that I've ever thought about it, hon.
A lot of new words too. What is abrasive?
Rough, like sandpaper.
I know that class is like getting sand.
Or Lippy with her students.
Yes. From my class.
All right, diamond is locked into this structure. These are locked into structure, so that's why they tend to be kind of hard. These just have LDFs connecting the layers, and so because of that, it's easy to break these off. And, well, yeah, but I mean, that's how your pencil works. You're leaving layers, but you're leaving layers of this behind. That is your writing. So if this didn't happen, your pencil, it would be like rubbing this over something. It's not gonna, nothing's coming off.
How do they make it stronger? Because like my sister uses like 0.09 or something, which is like extra thick.
I'm not sure.
And this one's 0.5.
I'm not sure if it's how they pack that, you know, if they pack it tighter or something. I don't know. I'd have to look it up. I'm sorry. I don't know that. All right. Molecular solids then are composed of distinct individual units. We call those molecules. That's where molecular solid comes from. They're going to have low melting points, and that is because they have relatively weak intermolecular forces, especially the ones that don't exhibit hydrogen bonding or dipole-dipole. They do not conduct electricity because their valence electrons are bound. They don't have any electrons that are available to move like the ionic compounds or the metallic compounds. Molecular solids then are sometimes composed of very large molecules or polymers, and oftentimes have hydrogen bonding. This is where like your lipids, when you talk about lipids, they're going to have a lot of these hydrogen bonds going on. You'll also have, you know, a lot of these hydrogen bonding, like we talked about yesterday with the DNA. Okay, that's what holds the two rungs of the DNA together. Okay. Examples of molecular solids held together with just LDFs, dry ice. That's why dry ice has such a low melting point, and it actually, dry ice doesn't even melt. At normal pressure, it goes directly from a solid to a gas, which is called sublimation. Yep. Iodine, sulfur, phosphorus, and then a bunch of hydrocarbons like octane and different things like that. But that wouldn't be a solid, would it? So, yeah, those aren't solids, though. I probably shouldn't have mentioned those. Yeah, you've got to be like higher up in the hydrocarbons to get there. And then polymers.
There's just like molecules that have already covalently bonded, and then they're just like sharing like really weak LDFs or hydrogen bonds.
All right, metallic solids then, you have your cations here, and then you've got a sea of electrons. So these electrons are able to move past. So you've got your group 1 metals and your group 2 metals. Your group 2 metals have 2 electrons that are able to move, whereas your group 1 metals only have 1. This is why a lot of your batteries are alkaline batteries, because it's twice the number of electrons versus here. They tend to be malleable. Malleable means that we can pound it out into thin sheets. They tend to be ductile, which means that we can pull them out into thin wires. We've also talked, I believe, about metal alloys this year. Yes. Okay. So, yep, we talked about substitutional, where they're about the same size, and we talked about interstitial alloys, where they're tiny. And this is where your steel is.
What's tungsten with carbon?
I don't know. You'd have to look it up.
Okay.
And then we have biomolecules and polymers. These are large biomolecules. They're non-covalent interactions typically, but because they're very large, they tend to be either liquids or solids at room temp. This is where, like, lard, if you've ever heard of lard, or shortening, okay? The fat that we have in our body, okay? Our fat is a solid fat, okay? Primarily. So, I mean, there's some oil in our bodies too, but as some of our hair shows after we haven't washed it for a few days.
I know.
But lard or shortening, or even we call ours adipose tissue, okay? It's just a fancy name for fat. Those are biomolecules that are very large, and that's why they're solids at room temperature or body temperature. Yeah, I have an excessive amount of adipose tissue. Yes. If you look at the protein here, you can find where those strands are attracted with hydrogen bonding. So nitrogen and hydrogen are attached, so they're going to be attracted here. There's your hydrogen bonding.
What's that weird squiggly?
Yeah, why is it so long?
It's just continuing on. They're just saying that this is going to be a big molecule. This is the beginning of it, and it keeps going, and then it comes back to here.
I don't like that. Why?
Okay, well, I'll get rid of it. There, problem solved. All right, here is just a comparative kind of idea of being able to look at a chart and be able to tell the difference between these. Typically, in order of increasing strength, now this is a typical, it's not an always, molecular solids, ionic, metallic, and then covalent.
Ionic and metallic are the same.
Approximately, yeah.
Covalent is crazy. So true. Biomolecules.
All right. Identify the type of solid in each substance here. CO2 is what? Right? What type of solid, though? Molecular.
Because dry ice.
And what is this guy?
That's covalent network. Yes.
Do we have to write covalent network or just network?
Or
You
just
write
covalent.
network.
You're writing it all out.
Oh, okay.
Do we have to add solid? Because they know what the type of solid.
Yeah, I guess here, if they're saying solid, you don't have to rewrite it. If they just said identify the type,
It's then you say.
then you would have to say solid here.
Oh, gotcha. Justify the different method.
Well, covalent network solids have stronger forces of attraction versus molecular. So therefore, the covalent network solid is going to have a higher melting point versus the molecular.
Okay. We classify CO2 and B and FES ionic, molecular, covalent, network, or metallic solid.
These we do's, in case I run out of time ever, these are where you can, or if you're reviewing, you can actually scan these QR codes and there's videos that show you how to solve all of the we do's.
Oh, damn. Okay, Aaron. Okay. Are you ready for the
A QR code app, yeah. But if you have a QR code, I mean, almost everybody has a QR code app on their phone, don't they?
My phone, no, like you can scan the QR code, but then you have to download an app if you want to watch the videos.
Really?
Yeah.
Oh, I thought it just linked right to them.
Your camera can take QR codes.
Yeah, you don't have to download a QR code.
Well, I used to, but I'm old, so.
I do.
All right. We are going to classify these and then arrange them in increasing melting points. So Cl2 is what? Molecular. Nickel is
Metallic.
boron.
Ionic. No. Wait, really?
Yeah.
It's not just
FES is.
I think. Now you got me second guessing myself.
Really? I just knew it was
Yeah.
two non-metals.
Hold on, y'all.
It's 3.
Well, if it's two non-metals, that's why I'm guessing myself. If it's two non-metals,
Oh,
it should be molecular.
borons. I don't know. Because that's like.
they're
Well, it's still-
electronegativity.
Oh, that's a covalent network solid?
Oh!
Electronegativity
Shama! You're kidding.
is not.
No way.
You're kidding.
It's one.
Oh wait, yeah, because then what is FES?
That was
That's
the
the ion. Yeah. So then it would go FES.
Oh, yeah. Yep.
FES,
Okay. Yeah.
nickel,
Let's go back up here and talk about that one. Bad lippy.
lipid.
I'm gonna go back up here.
No, it's not one.
Yeah, that wasn't the.
I understand, but we're gonna talk about it anyway.
But that one won't be on the test.
Right? No, I don't think it would be. So here it says other non-metal combinations with bromine or germanium. Okay, so that's boron and germanium. So that's where I missed that. My bad. Get used to it. I'm often wrong.
Let's continue to 3.3.
Okay, so this is going to be covalent network solid, and I'm just doing that for now. And then this guy would be ionic. Okay, so Cl2 is definitely going to be the lowest.
Do we have a metallic and do we have?
Yep.
Then
And this one, I actually looked these up. So this is going to be FES, but these would be easily like reversed if you wouldn't have looked it up. Okay. So these you could have had reversed, and that's okay. But then you should recognize that this, since it's a covalent network solid, is the most.
Yeah.
That makes sense?
Would it be okay if we just put like an equal sign between metallic and ionic?
Yeah, I don't. My guess is they would never give you both of these. They would give you one of them.
I'm gonna guess they would give you like the molecular, the metallic, or ionic, and then do.
I don't want you to think that that is a covalent network solid. So that's why I'm putting that line there. Okay. This belongs up here, and then this is the ranking. Okay. Does that make sense?
Right. Yeah.
All right. 3.3. Solids, liquids, gases. Particulate diagrams are pretty common to see discussing these. Okay. When you have a crystalline solid, they typically are arranged such that there's a repeating pattern here. And typically there's not space between these particles. So this is what a solid would look like. This jumbled up mess here, see how they're mostly together? They're not free and spread way apart, but they're sliding past one another. This would be a liquid. And then this would be an example of a gas. And a lot of times they'll have these little, I don't know what you call them. It's kind of like, well, it's kind of like that little kid on The Incredibles. What's his name? Dash? Yeah. You know, that would be something that would follow Dash. Okay? Because we're trying to show you that these are going to be moving faster than the solids or
I prefer the little bit.
okay?
Watch a movie on Friday and finish it Monday.
I think on Friday.
Thought we were doing Hangman.
Thursday and Friday we can watch a movie.
No,
All right.
we have something on Thursday.
But it's shortened, so.
Of the following, the best explanation for the fact that most liquids cannot be easily compressed is that,
Wait,
you know, compressed? Annie, you good with compressed?
Oh yeah. Oh sorry. Yeah.
What?
It's not. It's not D.
Okay.
I do agree. Yes, ma'am. Is it? What is it?
You tell me.
We said
Hey.
A.
No, they're all in constant motion. Everything's vibrating. It's not at absolute zero.
So it's not A.
Hey.
You're saying like you can't.
You're just going down the list.
No, he thinks it's
I don't think.
I think it's D.
You think
Wait.
it's D?
Of the following, the best explanation for the fact that most liquids cannot be easily compressed. Oh, most cannot be. Okay.
I have a pillow. Yes, they are relatively close together.
Well, that's what I said, and then you got mad at me.
No, I just said that you guys were just going down the list.
No, I said it wasn't.
My second choice was.
Are they-
and then you told me
yeah.
I couldn't do that.
Okay, draw a particle diagram that represents water in a puddle as it starts to evaporate. So we have water. Well, it's water, so some of it's liquid, some of it's gas, right? So we're going to have our water molecules down here as a liquid.
Yeah.
Can we just draw the circles?
No,
You can if you want. That's fine.
I do mom.
If it asks us on a test, we have to do it like that.
I would.
I don't know. I'm just trying to show intermolecular forces of attraction
I
here.
was doing
Okay. And then when we get up into the gas phase, then they're going to be spread apart. And there's not going to be any attraction between them. We can show our dashed lines that they're flying off.
Yay.
You're missing.
And they're getting bigger.
Dashed along.
They're flying off.
And
What if it's like a puddle of lemonade?
Where's your H's?
My
Oh,
H's?
those are
No.
circles. Those are your little circles.
So if you did circles, you'd show that they're, down here, but they're not really in a fixed arrangement at all. And then you would show up here as a gas that they're speeding off.
Yeah. the little line.
Okay.
Yeah.
Good? All right. Homework tonight.
What do you think?
3-1
We don't have
A or B if it's in there. And then all the way through the end of 3-3.
I don't see any.
I did all three of them.
Okay. Then I was wrong.
So just 3.1, 3.2.
Yep.
Okay, Alvin, you ready to do
The BS? Yep. And I uploaded the answer keys all as one document and made that a post. I'm not going to include it on every day's post now. You can just go to that one post and have it all there for the rest of the section.